Good afternoon, good morning, everybody, and thank you for joining this webinar, our first in 2019. And it's wonderful to kick off the year in such a way with this much anticipated webinar that we've been waiting for from Dr. Sininger, who's going to explore the topic of ASSR and how it can be used to quickly and accurately measure hearing thresholds in pediatric patients. Time to get started, so it's my pleasure to introduce our speaker today. For those of you who aren't familiar, I'll just provide you with a short synopsis of Dr. Sininger's esteemed career. So Dr. Sininger received her bachelor's degree in speech and hearing as well as a master's degree in audiology from Indiana University. She then received her Ph.D. in speech and hearing science from the University of California, Santa Barbara and San Francisco. Dr. Sininger then started her career and developed an interest in infants and children as a clinical audiologist for the University of Cincinnati Medical Center. After her PhD, she moved to the House Ear Institute in Los Angeles as a postdoctorate fellow in electrophysiology and later as the director of the Children's Auditory Research and Evaluation Center. In 2001, she moved to the David Geffen School of Medicine at UCLA to the Department of Head and Neck Surgery. And she retired as a professor in residence in 2012 and now runs her own consulting business. So welcome, Dr. Sininger, and we can't wait to hear what you've got to tell us today.
Okay, thanks very much. Good morning, or afternoon, depending on where you are. It's a beautiful day here in Santa Fe, New Mexico. I want to spend the next hour talking about the new Eclipse ASSR. I've had a chance to have some familiarity with it and to do a study with it, and I hope to be able to share that data and give you an idea of how this new technique will perform. First, I need to give you my conflict of interest. I don't work directly for Interacoustic or really any commercial group. I'm in my own consulting business. And I don't get any payment for any sales of any machines. I am rather enthusiastic about this technology, but I don't benefit from that enthusiasm in any financial way. But I did get money from the Oticon Foundation to fund a study that you'll see was very important to demonstrate the efficacy of this new technology. And I am paid by Interacoustics to give lectures and seminars here, mostly in the U.S. Here's what I'd like to get across today. I'm going to review the basic principles of ASSR. It's hard to know where you are as an audience in terms of how much you understand about ASSR. I know in the U.S. it has been not used very widely, and I think there are some misconceptions about what it is and how it might work. Then I'm going to talk about why we haven't adopted ASSR as a routine procedure, especially here in the U.S., because of the performance of some of the previous ASSR techniques. After that, I'm going to list the features that are going to distinguish this new technology, the Eclipse technology, from a traditional ASSR, and then show you clinical data to demonstrate how well it works. That we do have, in fact, improved test times, as well as excellent correlation with our standard, which is ABR, that will validate the use of this new technique. And finally, I want to give you a little idea about how they got there, the engineering behind the stimulus and the detection and the statistics and all of the incredible work that went in by the auditory scientists and engineers working with Interacoustics that achieved that end. Because I think it's important that we understand the technology that we're using. Okay, ASSR is not unlike ABR in the fact that they both use a stimulus to elicit a response. If the stimulus actually drives hair cells and drives neurons connected to those hair cells, then we see some activity that we measure with electrode. In the case of the ABR, we use a time waveform. So, as you know, there's a triggered stimulus, and right after the stimulus comes a snapshot of the EEG activity in the time waveform, and then those are added up. And if that final average matches some template that we expect to see, then we assume that there's a response. ASSR is doing somewhat the same thing, but in a different way. What the ASSR does is it takes its stimulus, so let's say, for example, 1,000 hertz. We want to test hearing at 1,000 hertz. And then it modulates that stimulus to go on and off at some known frequency. And the frequencies that we use for pediatric applications are generally around 80 or 90 hertz. So then the response detection simply looks at the spectrum of the EEG activity. And it says if those neurons of 1,000 hertz are being driven, then we should see some activity at 90 hertz, the rate at which those stimuli are being delivered. And so by looking at the FFT of the ongoing neural activity, we'll see a spike in the activity at the modulation frequency. So you can look at the amplitude of that activity, and you can also look at the phase relationships of that activity to see if there's a phase relationship to the stimulus. So truthfully, it is really a very clever technique. It has a lot of potential options that make it attractive as a clinical technique. Now, these are the traditional stimuli that have been used with ASSR. This is from an article in JAAA that I highly recommend. It's an overview article on ASSR, although it doesn't include, it's old enough to not include any of the information that I'm going to give you on the Eclipse ASSR. But the traditional stimulus was, for example, at the top here, a 4,000 hertz tone, and it's been amplitude modulated at 100 hertz. So by amplitude modulating 100 hertz, you would look for the activity at 100 hertz to detect this response. The difficulty with this standard amplitude modulated stimulus is when you look over here in the frequency domain, you'll see that it's quite a narrow spectrum. And the fact is that the spectrum that is that narrow has difficulty driving enough neurons. It doesn't cover a wide enough area of the basilar membrane to drive enough neurons to really be able to see a clean response. Now, you can also frequency modulate the stimulus. And this is an example of a frequency modulation. And it's hard to see, perhaps, but this is 4,000 hertz. And it's been modulated at 100 hertz. So it's going back and forth between 4,100 and 3,900 hertz. There's a change. And so here's the spectrum of that stimulus. So what most people have done is added the amplitude modulation and the frequency modulation into something called a mixed modulation. So this includes both, and that way you get your 100 hertz modulation that you use for detection, and this breadth of a stimulus. And the spectrum is now wider, which is better for detection. And there's one other way that's been used often, and that is something called this is a rate-gated stimulus. And here you've got your 4,000 hertz, and it is ramped the same way a tone burst might be ramped in time. And then it's presented every 12 milliseconds, which gives a modulation of 82. And then you get perhaps the most reasonable spectrum. It's wide enough to be able to see a response, and yet it's narrow enough to be fairly frequency specific. So these are the kinds of stimuli that have been used. We're going to talk about, when I compare stimuli to the Eclipse stimuli, mostly what's been used are mixed modulation and these ramped stimuli. Now, how do you detect the response? It's a lot like a distortion product otoacoustic emission, which you use all the time. And so this is the FFT, the ongoing activity. And it's averaged, same way it is with ABR. This is subject A. And there are two stimuli being presented. One of them is being modulated at 85 hertz and one at 95 hertz. And as we look at the spectral average here, the detection is looking for a peak at 85 and at 95. And when statistically, here's the statistical criteria down here, when statistically it is larger than the surrounding area, then we get a light up here. This is at 0.01, this one's at 0.05. After 8 seconds, then both are detected, and here even better. In this subject, it takes a little longer. 16 seconds, it didn't show anything. 48 seconds, you see a response at one frequency. That's how we use amplitude, and it's done with an F-test. So the amplitude of the activity at the modulation frequency is compared to the background activity, and if it distinguishes itself on the F-test, then we have a response. You'll notice here, we're only looking at amplitude. You don't see any phase information here. But if you extract the phase information on that 90 hertz, 85 hertz, or 95 hertz, you'll find that either the phase is time-locked to the stimulus, in phase, or we say phase coherent. And here's the polar plot of these waveforms. You can see that the phase is very tightly knit here in terms of the direction of the polar plots. But here there is, down here we have a no response because the phases are random. We want a coherent phase. The coherency of the phase helps to say, yes, this is something that is tied to the stimulus. Okay, so what are the potential advantages of using ASSR? People were very excited about it for a long time. And one of the main advantages is that, as I showed you, two frequencies being tested simultaneously, you can test up to 4 frequencies in each ear simultaneously. And you could potentially test more than that, but that's as far as the system has been evaluated. But it allows us to do all of the frequencies that we might want for an assessment on an infant in both ears at the same time. So could be a significant time advantage. The other thing is that the automated detection is going to give you a consistent result. With ABR, we do an average, and then in the vast majority of cases, we have to make a decision as to whether or not that time waveform matches some template in our brain. And so there's inconsistency across clinics, across people, in the way they make those decisions. But the decision is made by a statistic for ASSR, and so you have a result with a known sensitivity and with consistency. So why aren't we using it if it could be so wonderful? Well, the early studies found that ASSR, as it was implemented at the time, didn't detect responses at levels of normal hearing. It wasn't sensitive enough. And I'll show you data on that. So that's not good. We want to know when a baby has normal hearing. And it didn't correlate very well. The response you'd get from ASSR did not correlate well enough with a behavioral response. And in general, it couldn't meet standards that we'd already set by ABR. So we had a technique. We had tone burst ABR that was working very well. And so, at least in the U.S., the ASSR was not adopted, was not embraced as a technique. So, let me just show you some of that data. Here's a quote from Gary Rance. Gary Rance in Australia did a lot of the work with it early on with ASSR. And his quote says in the study that he did that it could not reliably differentiate between normal ears and those with mildly elevated hearing levels. It can't detect normal hearing, and half of the patients that are referred from newborn hearing screening, at least here in the U.S., will have normal hearing. Half of the subjects that we saw in our study had normal hearing. And so the idea of using a test that could not detect normal responses was not attractive. Here's his data. He did a study in which they looked at over the first 6 weeks of life on normally hearing newborns. And he evaluated 500 hertz and 4,000 hertz by ASSR and by ABR. Now, the ASSR are these filled circles, and the ABR are the open circles. And what I want to point out is that at both 500 and at 4,000, some of these normally hearing babies were showing responses that were highly elevated, much too much scatter for a normal hearing. Whereas the scatter and the distribution by ABR was reasonable. Here at 4,000 hertz, many responses up in the 50 and 60 dB range on a normal hearing baby, and that's just not acceptable. The stars here are from a study that I did quite a while ago with ABR, and so the threshold I got on newborns only right at birth was around 20-ish, right around here for 500, right around here for 4,000. And so you can see that these elevated responses are simply not going to be acceptable. I did a plot of all of these studies, and you know, they go back into the 90s and up through as far as 2014. Oh, here's one at 17. And these were normally hearing infants and children. And these are their average ASSR thresholds in hearing level. And as you can see, there's no consistency. The data are all over the place. And I attribute this to the fact that the stimulus had not been tied down. Do we use an amplitude modulated? Do we use mixed modulation? There was many different approaches to the stimulus, and there was confusion over whether or not to use amplitude as the detector or to use phase as the detector. There was a lot of infighting over which was better, when in fact they could have used both. A few systems use both. But the data itself shows why we have not been using ASSR. If it can't do any better than this with normally hearing, then it's not going to be trusted as a clinical technique. And here's just one more. This is on normally hearing adults. And as late as 2014, here is the predicted response, the ASSR threshold, plotted against the behavioral threshold for 5, 1, 2, and 4, and then all frequencies together. The perfect fit line is in blue. That I added that myself. But you can see that there's tremendous amount of scatter here, far too much scatter. These are hearing and hearing loss patients. Far too much scatter in the data between the ASSR threshold and the behavioral threshold. And finally, this is some data that compares the ABR standard that we were using to some early ASSR data. And by the ABR standard, I refer to the Stapel study, Stapel's, Gravel, and Martin, where they compared tone burst ABR thresholds to behavioral thresholds in a large group of infants and children. What you'll see here, this is just the data at 1,000 hertz. The ASSR responses are in the blue X's. The ABR responses are the red triangles. And here's hearing level. So this is the measured hearing level, the audiogram. And this is either the ASSR or ABR threshold here. Again, I put a diagonal. That's perfect match. You want to see data that is clustered around that diagonal and that has a reasonably good correlation coefficient. So one of the things we found was that there were no ASSR responses generated by the low-level stimuli. They don't even have any subjects down here because they could not see responses by ASSR down at the low levels. The ABR predictions, on the other hand, are good at the low levels, and there's many out here into the 80 and 90 dB range. So we see a good correlation across the range of hearing levels. The correlation of the ASSR, in this case by Maria Perez-Abalo, was an R-squared of 0.27. And you'll get a feeling for R-squareds, I hope, during this talk, but that's far too low. And that just reflects the fact that these data are not clustered around the line, they're scattered. Whereas the R-squared for the ABR was much better, 0.757. Those numbers range from 0 to 1. A perfect fit, which you would never find, but a perfect fit would be in the 1 range. So this is why, based on this standard, the ASSR was not adopted, has not been adopted. And this ASSR was done with just detection of the modulation frequency amplitude. Okay, as I mentioned, you can use phase, you can use amplitude, but many of the systems chose one or the other. Okay, so what does it need to have? What performance elements would this need to show in order to be acceptable? First of all, it has to detect responses in normally hearing infants and toddlers. It has to produce accurate estimates of hearing thresholds in all patients with hearing loss. And it has to be able to predict a 4-frequency audiogram in each ear during one natural sleep session. And that turns out to be about 45 minutes. I don't talk about it today, but I often go on and on about the importance of being quicker at getting these estimates, that if we could get babies evaluated during their first session when they're still young enough to be in natural sleep, then the whole process would move much more quickly. And so, in my estimation, any behavioral or any electrophysiologic audiogram prediction technique that we use needs to be able to be executed on a wide range of subjects in less than 45 minutes. So let's see how we can do. So the Eclipse version of ASSR comes along and it makes many claims. It claims that their stimuli are improved and they incorporate CE-Chirps, which we know will produce a larger response than a standard tone burst or amplitude modulated stimulus. They claim improved detection of the response because not only are they looking at the first harmonic, but up to 12 harmonics of the modulation frequency. They claim that they've improved the statistical analysis and that the logistics of how the program works have improved the speed of the assessments. All of those things should give better, faster threshold predictions at all hearing levels. So the question is, does it work? This is the title of the publication from the study that was funded by the Oticon Foundation. And the question we were asking was, how does Eclipse ASSR compare to best ABR on speed and accuracy in a real clinical study? This is published in Ear and Hearing, and it's open access, meaning that if you go to PubMed, search on Sininger Y, you should be able to do a few clicks and get a PDF of this article. I think it's also perhaps available through Interacoustics. This was just published last year. Let me just tell you a little bit about the study. We performed this study at 3 major children's hospitals in the U.S., one being Children's Hospital of Colorado under the direction of Deborah Hayes and Christian Uller, Cincinnati Children's Hospital under Lisa Hunter and Sue Windmill, and then the University of North Carolina Healthcare under Pat Rausch and Emily Spitzer. And I know these are names that you've heard before. Again, the study funded by the Oticon Foundation. Here's the design very briefly. We ended up evaluating 102 infants and toddlers. They ranged from under a month to almost 5 years, but the majority of these subjects were under 5 months. Some in anesthesia, about a third, and about 2/3 in natural sleep. We did 4 frequencies by ABR and ASSR, and the order in which we tested ASSR or ABR was randomized, completely randomized. So half the subject had ABR first and half ASSR first. Both of these techniques were using the same stimulus, the narrowband CE-Chirps, excellent stimuli. So they both had the advantage of this extra amplitude stimulus, which really enhances the ability to detect in a hurry and to see the response at very low levels. The ABR used an automated detection known as FMP, and we used a 95% confidence level as our threshold. ASSR also used 95% confidence, and I'll talk to you a little bit later about how that detection is set up. And both were run through the Eclipse system, so we had the same amplifiers, the same electrodes, same earphones. Nothing changed except the program that we were running. And we did both of the assessments in the same session. And the comparison measures that we used were the test time and the threshold level. So simple comparisons. And here's a very busy slide with essentially with the results that we got. To orient you, here's the 5, 1, 2, and 4,000 hertz results. On the x-axis are the ABR results, and on the y-axis are the ASSR results. Again, I've drawn this perpendicular, or this line here, saying that that would be perfect result. You know, if we got the same result by both techniques, they would all be lined there. These are bubble plots, and by that, a large bubble means there were a whole lot of data points at that same point. So the bubble size reflects the number of data points there. And as you can see, we had a lot of subjects with normal hearing. And that's because we just took all comers. And as with other studies, about half of the infants and toddlers that we evaluated did indeed have normal hearing. I talked to you a bit about R squared. R squared, now in this case, we're talking about the ABR versus the ASSR. And we got very good R squared values. 0.85, I think, is the lowest. So what that's saying is that these data are highly correlated. They may not be exactly the same number, but they are very highly correlated. And you can see at 2,000 and at 4,000 that there's many, many data points here that are right on the diagonal. And these have R-squared values of 0.95. Very, very good correlation. The difference between the data by ABR and ASSR is that in this study, the ASSR thresholds were slightly lower. These are the corrected thresholds, are slightly lower than the ABR thresholds. And you can see that there's a shift off the diagonal here. And the average difference was 9.3 dB at 500 hertz, and that's significant. It was 6 dB, 6.3 at 1,000, 1.7 at 2,000, and 0.8 at 4,000. Only at 4,000 were they not significantly different. Now, this is statistical significance. It may not relate to clinical significance. I see these data as very very clearly correlated, and differences can be handled with slight correction factors. But for the most part, what we're saying is that ASSR did equally well to ABR, and in some cases gave a slightly lower threshold. Both of these tests gave a really excellent test time. The average test time for all 8 frequencies by ABR was 32 minutes, but by ASSR was 19.63 minutes. And as you can imagine, that's wildly significant. Not only are we below the average 45, but by ASSR we were below 20 minutes. And so the test time, which are not reported as often as we would like to see in other studies, the test time was excellent, but better by ASSR, slightly better thresholds and a better test time. Now, this is, again, that plot of the normal hearing data. And I've added this time the plot of our data. Now, I also added this study here with the lowest numbers, and that it was done by Rodriguez and Lewis in Brazil. And in this study, they also used the Eclipse ASSR and exactly the same protocol as we used, except that we stopped at 10 dB. May not have been the right thing to do in hindsight, but the reason why our thresholds are slightly higher here at 2 and 4 is just because we didn't test any lower. They did test lower, and you can see how much better these results are than the previous results from other systems. This is the data, by the way, that's used for the norms, used for making correction factors on the Eclipse. So it really is the improved detection sensitivity, as well as the use of the CHIRP stimuli will actually lower the threshold by electrophysiologic means. I wanted to show one other study, and this study was published in 2009-2010. This was the last study that compared the previous ASSR technology to ABR. And so it is very similar to the study that we did in 2018, but will show a direct comparison between the Eclipse and previous good technology. Okay, so they were using a traditional ASSR and a traditional ABR. It was done with visual detection and tone bursts. Yes, they used the amplitude test at a single modulation frequency. The ASSR used Q sample, in other words, multiple samples of the harmonic. In this case, it's 12 samples, and it looked at phase and amplitude, and this is described in these studies. Their stimuli were cosine cubed windowed tones, okay, 5, 1, 2, and 4. The stimuli for our study are, and I'll talk about these in a minute, multi-cosine narrowband CE-Chirps with a modulation clustered around 90 hertz. Their ABR stimuli were real standard Blackman windowed tones, tone bursts. Ours are these same CE-Chirps, and we routed them at 39 per second. Both used infants and toddlers with normal hearing and hearing loss. They did all their testing on the same day. Ours was all done in the same session. So it's very similar studies, but the differences are those that I think will attribute to differences in outcome. So Van Manen and Stapels only reported a time estimate for their normal hearing, and that was here at about 23 minutes or so. For the normal hearing subgroup of ASSR in our study, the average time was maybe 16 minutes. So we're a little bit faster, but other than that, it's hard to say because the times were not reported for the subjects with hearing loss. And this is also important to note, is that our ASSR data show that it does take a little longer The normal hearing subjects are tested most quickly, a little longer for those with moderate, and even a little longer for those with severe hearing loss. But still, excellent time ranges. Okay, I replotted our data. So this is backwards from what you saw a minute ago. So now we have ABR threshold here and ASSR threshold here so that it would match with the Van Manen and Stapels data. And this is 4,000 hertz. And as you remember, our 4,000 hertz data, ABR and ASSR were very close. They didn't really differ by much. The average difference is less than a dB. In the Van Manen and Stapels, the ABR thresholds were lower than the ASSR thresholds by about 6 dB. Okay, so ours are slightly on this side of the line, and their data is slightly on this side of the line. But I also want you to note this cluster. Where the ABR thresholds were here is pretty normal. The ASSR thresholds are showing up at a wide range. And this is exactly the problem that we had seen previously. Too much scatter in the normal hearing subjects. Here's the same comparison at 500 hertz now. And as you remember, that's where we had the biggest difference. So if you take ABR thresholds are higher than ASSR by about 9 dB for our data. And it goes the other direction. It's minus 10 dB for their data. So theirs is all on this side of the line. Again, this big cluster down here where their ABRs are about normal. They have lots of ASSR findings. So I compared them all. So here's our study. In this case, it's ABR threshold minus ASSR threshold. So this is, the ASSR thresholds are better, lower in our case by 961.8. They're higher in the Van Manen and Stapels by 10.9. And that gives us a total difference score of 20 dB at 500. And what that says to me is that with the new technology of the Eclipse, we're getting 20 dB more sensitivity relative to ABR than we had in the most recent publication of traditional ASSR. And it changes a little over time, but the 500 hertz has always been the difficult to detect response. And so the greatest improvement in sensitivity is being shown here at 500 hertz, but there's an improvement in sensitivity at all frequencies. Now, this improved sensitivity doesn't have anything to do with the chirp, only because both our ABR and our ASSR measurements used a chirp. So this must relate to the sensitivity of the detection algorithm itself. Here I plotted just the Van Manen and Stapels normally hearing data. This is data from their subjects with normal hearing, and compared it to our data down here and then the data of Rodriguez and Lewis. And you can see huge differences in the assessment of normal hearing children. And this to me is an enormous difference and a huge advantage of the new technology, of the Eclipse technology. Okay, so how'd they get there? What are the performance elements that would make ASSR acceptable for electrophysiologic testing with infants and toddlers? Well, it has to have, as we said before, it has to detect responses at or near behavioral threshold. Well, we were able to do that. It has to be able to produce estimates, good estimates, for all levels of hearing in pediatric patients. And the Eclipse is able to do that. And it has to be able to predict 4-frequency audiogram in both ears in one natural sleep session, less than 45 minutes. And our average time was less than 20 minutes. And even with the hearing loss subjects was far less than 45 minutes. And so as far as I can see, if this is what needs to happen, it's already happening with the Eclipse ASSR. So how did it happen? Well, I want to go through a little bit of what they did, how carefully this was engineered to help you understand what was necessary to make this work and to understand how they made it work. So the first thing I'm going to talk about is the improved ASSR detection. As you remember from the first detection slide, there was two stimuli, and one was at 85 hertz and one was at 90. In their case, 95 hertz. And so the detection would look at the amplitude of those components relative to the background noise. But in fact, there are many, many harmonics of those components that are also produced and can be tapped for assessment. And so the new approach was to test not only 90, but 180 hertz, 270, 360, 450. And as you see, you get a diminishing return. But in the long run, the engineers have found that up to 12 harmonics of the fundamental will contribute to detection. And you can see it here visually that they would contribute. The other thing that, the other major change is to look at not only amplitude, but phase, both at the same time. So all that information is there. There's no reason not to look at it. And so, yes, you're doing 12 harmonics, you're doing amplitude, and you're doing phase, and that's for one frequency. You're doing that at 8 frequencies. So the computing power to do this is enormous, but it certainly is not past the capacity of our standard computers these days. And so this all happens in real time and allows us to get a faster result. Now, what about the stimuli? There was a tremendous amount of work that went into re-engineering stimuli, adding the chirp aspects of a stimulus, and building these stimuli in the frequency domains. They just started over to try and build the optimal stimulus for an ASSR. This article is well worth your looking at. It's in JAAA, and one of the things I really appreciate about this new technology is that things were studied carefully and published in places where audiologists can look at these studies and this data. So it's well worth looking at this. But I'm going to walk you through what they did to build these new stimuli. They started with a series of cosines. So now they're starting in the frequency domain, not in the time domain. And they created a series of pure tones, essentially, in this case clustered around 500 hertz. And these pure tones are separated by 90 hertz. Well, separating them by 90 hertz gives you a 90 hertz repetition rate. Okay, so that's pretty straightforward. And here, this is the time waveform then of this particular stimulus. And they decided to use 1, 2, 3, 4, 5, 6, 7 of these cosines. So they took it a little further, and by reducing the amplitude of the flanking cosines by half, they were able to get rid of some of this ripple here between the stimuli. Now, one of the things that using these cosine stimuli did was it broadened the response right at, this is for 1,000 hertz now, but right at the center frequency, you're getting a little broader, flatter response, and then a narrower response down here on the sidelines. And what that did was it just improved. It just gave a little extra burst to the amplitude of the stimulus because you've got a few more neurons right in this range being activated. Okay, so it's got a nice narrow 1 octave spectrum, and yet a little extra burst here. So as compared to a regular tone burst type of a stimulus. Okay, I want to talk to you about the chirp characteristics. How did they add in the chirp characteristics? And I'm going to give you a little brief background on chirps. The chirps are a way of counteracting the traveling wave. And if this is an unrolled cochlea, if you activate it with a click stimulus, you will see that the high frequency neurons are activated first, following by the mid frequency and the high frequencies, and there's a time delay there. And that time delay will cause some problems with the amplitude of the response. So let me explain that to you. So here's a broadband chirp. The time delay is counteracted by starting the low frequency elements of the chirp before the mid frequencies or the high frequencies. So since this takes a longer time to reach activation, you start it up first. And that way, all of the neurons should be activated at approximately the same time. Now, how this is built is very complex, and it's based on a lot of data on the human cochlea. So this has to match the time delay within the cochlea. And the reason for doing this, that I like to use Manny Don's stacked ABR as a way of demonstrating this. But what he did, he was able to extract frequency-specific components using high-pass masking of the click ABR. So here's his click ABR. And by using high-pass masking and subtraction, he could find the element of this ABR that was generated at 11 kilohertz, at 5.7, at 2.8, at 1.4, at 0.7. And he noticed, as we've all noticed with tone bursts and other techniques, that there's a shift in the latency of wave 5 as you go into the lower frequencies, and that's because it takes longer to get there for those regions to be activated. And simply by taking these time waveforms and shifting them in time so that wave 5 would be lined up, and when you add all these up, you get this. When you add all these up, when they're lined up, you get this. And so you can see more amplitude, and that's because you're not getting phase cancellations. You can see how this negativity here, when it's added to this positivity, is going to cancel out some of your amplitude. By lining them up, you don't. And it's the same kind of concept that's used in a chirp. So, and here is just, you don't see the time waveform on an ASSR, but if you could, you'd see that a 30 dB chirp will produce this amplitude response, whereas a 30 dB click is there. Here's the same thing at 50. And so incorporating a chirp into the ASSR stimulus is going to allow for a bigger response, which makes it easier to detect and faster to detect. So this is the data on which the chirp was developed, the broadband chirp. Okay, and this is data from Manny Don's lab, again, based on latencies. In this case, these were narrowband ADRs. And so this function was fit, and this is the delay function that's used for a broadband chirp. Well, that's great. What we need is narrowband stimuli. And so, and these, we're back now to our development of these stimuli. And so here's the stimulus as it is with these frequency components at those levels. But now we want to build in a time delay. So we want these stimuli to occur first, followed by the higher frequency stimuli. So if you look at the time delay simply right around any one of these frequencies, this is 500 hertz, then you can imagine how much of a delay needs to be incorporated. And the way that that was done was by altering the phase of these components. So by simply making a phase change that would impart the same time delay to these stimuli. You can't see it here because this is just a frequency, a line spectrum. You don't see any phase information. But pretend you can, and pretend it's that these phase delays have been added, and now the stimulus is going to look like this. Here it's very symmetric before the phase delays. Here you see they're asymmetric, and if you look closely, I think the next slide has it, you can see that there's maybe a little lower frequency followed by a little bit higher frequency. It's not as obvious as it is in a broadband stimulus. But this is the way that they imposed a chirp characteristic on the stimuli that they wanted to use for ASSR. Now, one final thing. This is all fine, and here's how the stimulus stands right now. But in careful looking, they found that the detection frequencies, since they were using multiple harmonics, and they were all at 90 hertz, for example, was going to overlap with some of these frequencies, and that's not good. We don't want our stimulus and our detection looking at the same frequencies for fear of stimulus artifact. So with a simple shifting of these frequencies by 45 degrees relative to these, then now there's no overlap between where we're trying to detect and where we're stimulating. We still have essentially a 500 hertz stimulus. And by shifting it by half of the 90 hertz, we also get an alternating polarity stimulus. So all of these things were tested as each element was being developed, and to just ensure that this type of a stimulus was going to be able to do what we need it to do. And this is what they look like, any one particular component. And you can see now in the narrowband stimuli, they look a little like tone bursts, but you see a little low frequency edge and a high frequency edge. Here's the low frequency edge and the high frequency edge on these stimuli. These are the same stimuli that have been implemented for ABR, except in ABR they're just cut as tone bursts. You can use whatever stim rate you want. Here's the nice spectrum, flat across the top and narrow in this region, and they're all about an octave wide. Okay, we're getting close to the end. The other thing that I want to talk about is the way that the responses were detected. As I mentioned, we used a Q sample. In other words, multiple tests of the modulation frequency at the harmonics. And this is another article that I can recommend to you. And in this article, they were comparing the type of stimulus that was used, the ASSR statistic, and the number of harmonics tested. So they were looking at your standard stimulus as compared to these cosine stimuli. They wanted to look at whether or not phase or amplitude or both were being assessed. And they were looking at assessments with 1 harmonic versus 6 harmonics. Here's the detections with 1 harmonic and 6. And these are with the AM stimuli and the cosine stimuli. Well, you can see right away the cosine stimuli gave a higher detection, and that 6 harmonics gave a higher detection. Now, I want you to note that at this point, we're not at 100% detection with a 30 dB, but the stimuli were not chirps yet. They were simply the cosine stimuli before the chirps had been added. So if you add the amplitude advantage of the chirps, we should be getting detection to be very close to 100%. Test time, we want low test time, and it's lower for the cosine stimuli than it is for the traditional. It's about the same for 1 and 6 harmonics, but remember you get a big advantage on the 6 harmonics in terms of detection. And then overall performance is by far the best with 6 harmonics and the cosine stimuli. So they did a very careful check of whether or not these components were actually adding to the response detection. Here we've got whether or not the components that were used for detection. Some were phase, by rate, by rank, some were phase and amplitude, but by far the best performance, 3 point something, was with phase and amplitude using these cosine stimuli. Finally, there's been some protocol enhancements that I think are really worth mentioning. This is the ASSR table for that you see as you're doing the testing. Right ear, the left ear, 5, 1, 2, and 4. All these tests can be run simultaneously. And you can independently control what the levels are in each of these quadrants. Now, you might want to maybe start them all up at one level, but as you can see, here's the time across this axis. In this case, 500 reached a response at 60 before a minute, whereas in some of the other examples, here 60 takes more than 2 minutes. Well, you don't have to wait for all of these to reach 60 dB response or no response before you retest. As soon as a response is made here, you can click in this area and set a new level and start up a new level. So all of these are being run independently. There are some limitations as to the level differences that you can impart during the test between one frequency in one ear and another frequency. But within those limitations, you can continually change the levels until, and when you finish with one frequency in one ear, you can then continue to work on the other frequencies. And that dramatically improved the amount of time that it takes. There's another feature here. If you get out to 6 minutes and you don't have a response, you can add a minute or 2 or 3 in the hopes that maybe you will receive a response. And so, and there's data down here that's constantly being shown. So that, I think, contributed dramatically also to the test time. But in conclusion, I'd say that we found in our study that the Eclipse ASSR was slightly more sensitive and much faster than a very nicely executed ABR. We did ABR as best we could. The reason for that is because there have been carefully designed and implemented improvements in all aspects of the technology, and you can read about these and you can see how carefully everything was redesigned by the engineers. And that's the reason why it works as well as it does. And I have to say that were it my choice, I would choose this as my first test on infants and toddlers to follow up on newborn hearing screening, or for whatever reason why we need to predict an audiogram on those young'uns. And I'm happy to take questions.
Okay, thank you very much, Dr. Sininger. That was a really insightful webinar and full of really interesting data. So I hope everyone enjoyed that. I have opened up the question area now, so just seeing if anybody has any questions. So we've got the first question coming in, and it says, thank you for an excellent lecture. What do you feel are the challenges for this new generation of ASSR to overcome and be more accepted or used in the assessment of hearing impaired infants rather than ABR?
Yeah, we had that same discussion. Interacoustics brought together a group of high-level audiologists and showed them some of the data and asked that same question. And their answer to us was, we need a published clinical study. And that's where this study that I did arose. So I believe that you have to have the data. you have to actually use it and see how it works and compare it to your standard. So we did that. The ABR performed very well. So there may be people that will stay with their ABR. I hope if they do that they choose to look at chirps, because that really enhances the response, as the folks in the UK have shown us. But other than that, I think it's simply a matter of what the needs are. And when I lecture, I like to talk about the responsibility of audiologists to get these assessments done very quickly, so that families don't have to come back multiple times, the clinics don't have to have multiple appointments, that the normal hearing children can be dismissed and their parents can be given that good news. And so I hope, as everyone accepts that responsibility, that they will look for technologies that will allow them to do that.
That's great. Thank you very much. The next question is, I think it's important to note that the study mentioned ABR versus ASSR was done with both CE-Chirps, and the ABR was not the traditional tone burst. We assume that if the tone burst had been used, that the test time difference between the ASSR would have been significantly longer.
Yes. It's really clear, and again, the folks in the UK have really shown this the best, that the responses are bigger. And if you're using something like FMP, so you don't just have a fixed number of sweeps, but you stop when the response is robust, and you get a bigger, better response with the chirp stimulus, then that's where you really see the time advantage of using that type of stimulus, because we will stop at 600 sweeps if there's a response, and that was often the case. And you wouldn't necessarily do that if you were using a fixed number of sweeps. So I'm a firm advocate of using something like FMP, and as far as I know, it's only implemented properly on the Eclipse. I'm a firm advocate of using something like FMP, and when you use it with those brilliant stimuli, it's all going to be faster, and that's the reason why we got such good times for our ABR part of the study.
Excellent. And there's one more that's just came in. It says, "Thank you for a great and well-documented presentation. Are there any patients you would not recommend performing ASSR on?"
Yeah, if you suspect auditory neuropathy, this isn't going to help. But I also don't recommend using tone burst ABRs with auditory neuropathy. In either case, you can't really get a good audiogram estimate if you expect that it's a neural type of a hearing loss. So and let me just give you one little hint. One of the things we did was before we tested any baby, we would do a broadband chirp ABR and get a threshold. And it did a lot of things. First of all, again, we had so many normal hearing babies that we got, 10 dB thresholds on so many of them. And it gives you a chance to look at a standard ABR and get an idea of whether or not you're looking at potential for something like auditory neuropathy. We also did our OAEs and our middle ear measurements before we started. So we had a lot of advanced information. But you can't use ASSR to get an audiogram prediction if there's neural involvement.
Okay, thank you very much. I think we're just getting one last comment through. Some audiologists continue to hang on to having visual of the ABR and can't trust the ASSR because of that. What would you say to these audiologists?
Well, having a visual is a nice thing, but certainly if you read all of the studies that have been done on the ASSR, and you understand the confusion that can be caused by depending on a visual. I think you have to be the sort of person that really understands and believes in those detectors. They do work. And on top of the fact that we're living in a time where medical legal issues come up all the time. I personally very much like having a backup. I like having be able to show the published data and be able to show that I used a standard technique based on good science and good published data, and that this is the result that I obtained. And I think that's going to not only give us faster results, but it's going to give us results that we can justify completely. I've seen too many poorly interpreted ABRs. And I know there are many, many audiologists that can just do it and do it in their sleep and do it perfectly. But there are others that can't. And so I really believe we need to adopt a standard that is less arbitrary.
That's great. Well, I won't take up any more of anybody's time, and I'd just like to say thank you again, Dr. Sininger, for taking the time out of your schedule to come and talk to us today. I think we found it really rewarding. And yes, if people do have any questions that come to mind after this session is closed, then please feel free to email the Academy website at academy@interacoustics.com, and we'll be happy to answer those questions. But this just leaves us to say thank you very much for tuning in today. And again, thank you, Dr. Sininger, for your fantastic talk.
Thank you.